Good afternoon. My name is Recep Avci, sorry, and I'm going to be pointing with this pointer here to the things of interest on my slides, hoping that this will be visible to everybody, including those that they are listening through internet. So my name is Recep Avci. I am the director of Imaging and Chemical Analysis Laboratory. If you click this link, I really recommend. This is our MONT Montana Nanotechnology link, where there are lots of information. This ICAL is part of 4 core facilities that fall under Montana Nanotechnology facility, which is one of 16 national centers that is under NNCI, National Nanotechnology Coordinated Infrastructure. Montana is one of these 16 centers throughout the country. And I would also recommend to visit this site for another reason, in case that you like what I present today and you would like to collaborate or do some proof of concept experiments using our facilities here. You can write one page, particularly this is true for new users. Submit it, we will go through it and then support some part of your expenses associated with your proof of concept experiments. Hopefully, if you find it useful, then you can continue working with us. So let's see. The topic is integrated OHJ nanoprobe. So the OHJ comes from this scientist, a French physicist. He discovered cosmic rays and then the phenomena of OHJ transitions. The point of using this word integrated OHJ means that there are additional components attached to this system that makes it really very powerful analytical tool. So I will go back to fundamentals to tell you why this is important. So typically an OHJ nanoprobe is a sophisticated electron microscope, except that it works in ultra high vacuum conditions, 10 to the minus 10 or 10 to the minus 9 type of torr pressures, as opposed to sophisticated field emission electron microscopes. They work in high vacuum conditions, which is 10 to the minus 6 to 10 to the minus 7 torr pressures. So the integration means we add additional analytical tools to this system that we purchased a couple years back. The reason these systems are expensive because they are ultra high vacuum systems, all made out of stainless steels. Even these 2 additional detector capabilities that we add has to be compatible with ultra high vacuum conditions. This is an X-ray system here. This is electron backscatter diffraction system. In addition to that, OHJ came with argon ion gun, which is not available in the scanning electron microscopes. And obviously, each scanning electron microscope will have secondary electron detector, X-ray analysis capability, and an EBSD. However, they will not have this OHJ electron analysis capability, which is concentric with the electrons. They are generated from a field emission gun up here, and focused on a sample nearly about maybe 75 centimeter to 1 meter down there. Here is the picture of our system here. This system here is enclosed inside this metal box, which has thick metal walls. That's for acoustic isolation as well as light, as well as we bake this system to achieve high, ultra high vacuums. So this sits in this prison here, so to speak. We control everything from outside. And speaking of control, there is a sample here. We can manipulate it. XYZ rotation. There's argon ion gun, which is unique to this system right here. There's an EDX detector. It's an X-ray detector, essentially, which is integrated into the system by design. This system is kind of unique. I don't think there is another one like that I know of anywhere. Now, OHJ exists everywhere, but the point is that integration of these other analytical capabilities is unique to us. And so there's a camera here, a digital camera that takes pictures of diffraction patterns to tell about the structure of the crystal structure, orientation, and phase identification purposes. This is the link to ICAL, and you can see all of it in the MONT web pages right here. So let's start with an image here, because what I will do today is I will contrast. I was told not to leave this area because my voice is apparently in this cone here, so I'm imprisoned here, so do forgive me. I like to go there to talk, but I cannot do that. so I'm kind of have to do this. So here is that image that all sophisticated field emission microscope can obtain. And then you can also do elemental analysis. These days, this elemental analysis is such that, for example, you can take a full spectral analysis at every pixel, which you can divide this field of view by 1,000 pixels. So you will have some like 1 million spectrum taken. Within 5 minutes, you can essentially analyze, and then you can go respectively say that I want to have an image or distribution of certain element that you didn't figure it was there. You can mine this data. So these are everything can be taken in less than 10 minutes. So this is the elemental map, and so you can see this was a polished steel surface, carbon steel everywhere. Your knives to your engines to heavy equipment to buildings, they all have iron. We cannot do without the carbon steel. And so this is when you polish it, in this, when you zoom in, this is how it looks like. This is a manganese sulfide inclusion. About this manganese sulfide inclusion, they are long, they are thin. For example, cross-section here is less than a micron, maybe about half a micron. Length could be hundreds of microns. These are called hundreds of microns. These are called the stringers. They are in the steel by design because they are scavengers of sulfur. Sulfur is bad for welding and anything like that. So quality of the steel can be judged by quality of how much of this sulfur you clean from the ball. So you can see this seems like a manganese sulfide. This is a manganese sulfide, and there's some titanium here. You see, there's excess oxygen. We sputter this thing. Sputter means we have argon ion gun in a gun like sandblasting. We can remove sub-nanometer material from the surface and look what's underneath of it. So this is how it looks like. And these are the carbide features right here, because they put carbon in these steels to make it hard. Otherwise, pure iron will be very soft and very expensive. So, so we can do this much with all sophisticated field emission microscopes, even with other non-field emission microscopes. You can do elemental analysis using X-rays very easily. So now the next page is very important. This is where I will explain, this is how technical I will be, just simply by pictures explain why this much of information is not enough, because system gives more information. All you have to do is find it. So this is I just made this thing. All electron microscopes work on a very simple principle. You generate high energy electrons up to maybe 30,000 eV. Typically we use 10,000 eV or 10 keV. very narrow energy band, typically maybe 0.5, 0.7 EV resolution here, you essentially strike the surface with these electrons. Well, what happens when an electron hits the materials of interest? It ricochets, it scatters throughout the volume, and essentially it stops, and it generates this interaction volume. Depending on the materials and the energy of this, typical interaction volume for an iron, say, for a 10 keV beam will be less than 300 to 400 nanometers. So they will penetrate into the system, and in doing so, generate a bunch of information. So this is what comes out. I put here as a function of energy. Here it was pure beam, but here on the right side, what comes out in terms of information. So these electrons, when they interact with an atom in the volume of interest, they occasionally go there and knock one of the deep electrons in the core levels of an atom. So it goes into the system, it disappears. It has no importance for this kind of application. But what happens that atom looks at it and says, oops, I have a hole, lack of electron right there deep, and the economy of nature is ruthless, nothing like what we have these days. It immediately solves that problem within 10 to the minus 13 seconds. It says, I have to fill that hole. It's unrealistic, unnatural. So what happens is that one of the electrons, very near to that hole, essentially within the atom, fills that hole. That's where the information starts spilling out, gushing out. So extra energy released as a result of this electron filling the hole are two things. X-rays are emitted, say 75% of the X-rays emitted, but other 25% of the time, OHJ electrons are emitted. Their energy typically runs from 0 EV, well, say to 20 EV all the way up to 2000 EV. There's a loss of information. They are specific to that material that from which these OHJ electrons come from. Same as these X-rays. Like here's an example. This is an X-ray coming from a steel sample. There's iron, there's chromium, even some aluminum here. Similar OHJs are also very specific. Their kinetic energy are fixed from 0 to here. So most of the time people ignore it. Not only do we ignore it in most of the sophisticated X-ray analysis, I mean the elemental analysis, they are expensive. There's a reason for it. You cannot sell these systems if it turns out to be $1.5 million. So, so occasionally with people like me, you can raise this money after 4 years of working. It's not trivial. But the point is that we now have, so not only can we have information from these X-rays, we can have information from these OHJ electrons. The thing is different, you know, the take-home message today is that these electrons, some of them actually come out and generate this curve. Electrons pertaining to these OHJ electrons are coming from very top surface, first a couple of nanometers. They give information about the surface. Whereas these X-rays can penetrate through this thick volume, it gives information about the bulk underneath. So now we cover two worlds. Materials interact through their surfaces. So you need to have information. I will give you lots of examples. And then these electrons up here about the same energy, they give this diffraction pattern. So you can do backscattered electron spectroscopy, which is a very powerful technique. I'm not going to talk about it, but you can also get these pictures, diffraction pictures, if the surface is nice and clean. It gives information about the structure, orientation, and phase identification at sub-micron spatial resolution. And most important thing I would like to talk about, these slow electrons right around 100 or 50 to 100 EV. These are the least penetrating electrons. These are the ones they use to make these beautiful scanning electron pictures, low energy electrons. The reason for that is, I won't show you any other technical thing, and I'll show you nice pictures from now on. And then because here I show you the mean free path or attenuation of electrons inside solid. These are some examples of various solids versus their energy. Our energy of interest is from 50 or maybe 30 all the way to 2000 eV. You can see electrons around 50 to 100 are least penetrating. That's why you see these very nice sharp images, very high depth of field, because you cannot get information below, say in this case, half a nanometer from these electrons. So that's why information comes from the surfaces, produces this beautiful depth of field. I'll give some examples. So, so that's the take-home message. X-rays give information from underneath the surface. Electrons give information, OJ particularly, from the surface. Here's some example of, this is a pipe sample sent us by ConocoPhillips. It was in Nordic Sea, in the gas and petroleum applications. Corroded. You can see these are iron sulfide deposits like horns. And you can see this is way above the surface, and I can get very similar kind of resolution. So depth of field is due to that low energy electrons. You collect them, generate these images, and it's automatic. You don't have to, like an optical camera, there's a small hole and things like that. Here's another example. This is way above the surface, several micron, and this is up here. The surface information is contained, and then the electron beam doesn't change too much of its focal properties within this distance, so you get this three-dimensional effect. So let's go back to the OJ, what we can do with OJ. Here is one of these manganese sulfide inclusions. Again, these are long and thin. Length comes from, because when these steel, during the production, when it's hot, they roll them to, to make a bar like that, for example. So during that process, rolling process, you have this elongated manganese sulfide inclusions. The importance of these is that they cause also localized corrosion, pitting, and things like that. So we have to understand them very in atomic scale. So here it is. I'm taking a spectra from this location using OJ. You are not familiar maybe with OJ like you are familiar with X-ray, but that's how it looks like. Typically, they present these things by taking derivative of these, but I don't like it too much. As you can see right here in this yellow rectangle, there is copper on this surface, there is manganese on this surface, there's iron on this surface, and there's oxygen here, and carbon here, and sulfur here. Good. So I go to the next, about 1 micron away from, even less than 1 micron. This is, yeah, it's about 1 micron away from here. I can see what I expect to see: iron, oxygen, and carbon. Good. But let's just now look at the mapping of one of these. So, okay. You see at the bottom here, I do use X-rays in the integrated OJ. When I look at that, I just map sulfur and manganese. I can map anything on the periodic table, even after I take the data. And so, no surprise, that's what we thought for many years before we had the OJ. So, oh, okay, people say this manganese sulfide for the last 40 years, 50 years, so it's manganese sulfide. Wrong, as wrong as it can be. Here is when we do the same imaging using OJ. This particular case, it's always not like that, but we expose this surface to some chemicals. You can see the sulfur is bleeding away. It's on the surface. This information is very important in real life application, but you would have missed this one if you didn't have surface capability. This information comes from the electrons, not from the X-rays. Apparently, manganese is not doing it, just the sulfur. So sulfur is apparently, you can actually exchange it if you have the right price. So apparently, the sulfur leaking from this manganese sulfide inclusion around there, perhaps this is a very thin layer of iron sulfide now. So not only that, so you cannot do that using sophisticated field emission microscopes. You cannot also do the following. We go, for example, another manganese sulfide inclusion. This time, we are looking at the top of it, this way, cut and polished. Here is the manganese sulfide inclusion block. Yellow square we are analyzing, doing depth profile only from this area. And there's another white point. We identified that to be a copper containing sulfur, copper sulfide growing parallel to this axis with the manganese sulfide. But so when we look in here, there's EDX did not show any sulfur here, but when I look with OJ, I see the sulfur. So we do depth profile. I send this argon ion and then sputtered it. You can see there was on that surface up there maybe 14 nanometer thick copper, which I didn't know. It's very important in electrochemical reactions. And obviously the copper is removed now. There's not much left, and sulfur increased, and the iron and manganese increased a little bit. So this would not have been possible in the standard high, and field emission microscope because you don't have electron microscopy. And here's another. I will give many examples of just to bring about what you cannot do with OHJ Nanoprobe. Here is the tip of a manganese sulfide inclusion in iron again. And so we do depth profiling in this area here and in this area here. Depth profile in this area are these dashed lines. So let's look at the depth profile of iron, typical iron surface. You can see apparently there was a 10 or 9 nanometer of oxide. This is a native oxide. It's not surprising on the surface of this ferrite structure. And then nothing else. There's no manganese and sulfur here, obviously. And then iron increased, and now this is pure iron steady state. On the other hand, on the manganese sulfide, we didn't know this. In fact, this is not even published. Nate is the graduate student of mine doing all of these, so I'm taking the credit, but he's the guy has done all of these. And he's the guy who also teaches this system, the use of this system to anybody who wants to use it. So here is the oxygen. There was a thick layer of oxide on the manganese sulfide inclusion, which I have no idea this was supposed to be there. It was about 29 nanometer deep. And then the sulfur then finally increased and becomes steady state. So surface of this lacking sulfur has oxygen. So, so the question is, there's oxygen on the surface, there's sulfur on the surface, there's iron on the surface, there's manganese. Which one is pairing with which? So I'm going to give you another example. This is very unique to OHJ. We can do chemical mapping, not just elemental mapping, but chemical mapping. You can see here, this is a clean iron. This is a profile of one of the OHJ transitions at around 51 eV kinetic energy. But if the iron is oxidized, its profile is different. The one looks like on the left. Similarly, you have manganese. They have a different profile if it's oxidized. So I'm taking advantage of this difference. I'm now mapping the iron oxide, not just iron, not just oxygen. You see, surface said no iron oxide. Everywhere has, and this is obviously expected to be iron oxide rich, but here there is no iron. So this oxygen is supposed to be pairing up with manganese. It's totally surprising, totally unknown. Here it is. We run the manganese oxide map. It's nowhere except on these manganese inclusions. There is no way you can do something like that in just using X-ray analysis. Okay. And we can also map it. This is, I put it there for the heck of it. You can see wherever there is, this is a manganese sulfide inclusion, this time, parallel to the rolling. And when there is less sulfur, there is more oxygen. These are, and they are not uniform. Some areas have this, some areas don't. These kind of information is impossible to obtain with any other, and they are very important. And another one, which is I'm very proud of it, we published this thing, is that we found the match in a forest fire. We always wanted to know where the corrosion initiates in a manganese sulfide region. So here is a manganese sulfide cut and polished perpendicular and exposed to a corrosive environment. This is about maybe 300 nanometer diameter here. This is the sulfur map, and this is the oxygen map. We polished and then exposed this surface to anaerobic conditions. There is no oxygen. In fact, as a physicist, I did double strength anaerobic. There's no oxygen in the system, and we spotted the surface just to make sure that there's no oxygen, as you can see, anywhere on the surface. But it seems like using OHJ, I have a ring of oxygen here. It shouldn't have been there. System was never exposed to oxygen. We spotted anything on the surface. Now there is a ring of oxygen here. As it turns out to be, this is the match in the forest fire. This is where, you know, the corrosion started, because there are ions are coming out due to corrosion. They react with the water and deposit this iron hydroxides. And right here in the immediate surroundings, without OHJ, you would have no chance. You will see something like that. And then they grow after that. They become pits along the manganese sulfide inclusions, and they coalesce. So these manganese sulfide, the pit is growing here. It's the micropit. When the acidity increases, this starts dissolving, generating abiotic sulfur and hydrogen sulfide, and then essentially the pit grows. And one of my students used to be Brett, did a thesis on that. And then he counted these manganese sulfide inclusions inside this carbon steel. There were 3,400 minus plus maybe 50% manganese sulfide inclusions per square millimeter. So there are areas that they are very rich, and then they coalesce as they do the typical separations, like 10, 15 micron, and they give rise to these macroscopic disasters. Thanks to OHJ, we were able to explain it all the way to the molecular level. And here's another example. Some people work with bacteria, and then they have these appendages, pili-looking things. In this particular case, these are involved in electron transfer to and from bacteria for their metabolic activities. Our idea was, can we elementally, can we see what elements, is that probably proteinaceous, but we want to look at the elemental composition. So here is an image of them. Here is the carbon map. This using X-rays. We use 10 keV. And there's no evidence of mapping here because 10 keV goes right through a couple nanometer thickness of this, doesn't generate any X-rays, so you cannot image it. But OHJ being surface sensitive, you can see we can map any element you want. And I'm going to give another example of what you can or you cannot do with OHJ. This is something that we have been working with graphene these days, and it's a huge deal. It's, they think it's the material of future. Europe has a roadmap for graphene science and technology. That's a $1 billion project, 10-year, started from 2013, will finish in 2023. There are 150 scientific groups, 23 countries, and this is just in Europe. Imagine, same thing happening in the rest of the world. They start from discovery and applications of it to various very valuable things. Hopefully, we will see them in our hands, from flexible screens to solar cells to fast batteries that will charge your whatever car or cell phone within less than a minute and things like that. Read about it. It's a remarkable material. So what we want to use this material in our laboratory, can we coat the surfaces with this so this is graphene, one two-dimensional, highly conductive, highly flexible, extremely strong material. Put the one monolayer of it on the surface, or a couple monolayer of the surface, so we can use it to protect these materials against degradation. The idea is this, just like a tablecloth, instead of putting on a table, we will put on an insulating, for example, material to prevent charging. If I had that, I don't need to worry about using my OHJ in any materials, but OHJ cannot be used in insulating materials. You have to put a layer of thin material on it, and that's useless. OHJ simply sees what you put there, it won't see anything at the bottom. So there's a limitation. So what I will show you that you can never do with the standard high-end field emission microscope is that when we look at these, there are three samples. One was one monolayer copper coated graphene on copper foil. The other one was 6 to 8 monolayer graphene on copper. The third one was a very thick layer, 1 micron graphene on nickel. So when we take them out from their containers, the 6 to 8 layer and then multi-layer, they came in air. They were exposed to air. I didn't see any oxygen on them too much. This was packed in a vacuum pack, and because of 1 monolayer, and they claim it's uniform across. So there was some oxygen here. And then I kept it a day on the table, and then oxygen started increasing. Well, graphene is supposed to be preventing that. You know, how the heck this oxygen is going on my copper surface? Is it going through graphene or is it going through imperfections? So I did depth profile, or he did depth profile. So here is the graphene. It was typically 1 monolayer of graphene is about 0.3 micron or 3 angstrom thick. So we finished it within 0.3 micron as expected. Graphene is gone, but oxygen was still there. Created a native oxide on copper, 2 nanometer thick. Only after 2 nanometers of sputtering could I then have a pure copper, which is these two. No way you can do something like that with anything but these kind of systems, OJ. And I'm almost done. We will give you plenty of time for questions. Dave asked me, don't speak too long, so I listen. So here is another example. We saw this inclusion in on a carbon steel, and then we analyze it. It suggested it's titanium nitride, and then we do EDX. Most of the peaks in the titanium and nitrogen kind of, and even oxygen kind of on top of each other. So combining these two techniques, we decided that was a titanium nitride, but which one of many titanium nitrides? David Mock here in the audience, expert in this area. So there are various different structures. So what we did, we used backscatter electron diffraction, did the orientation map. This is the key here. The red areas are 0, 0, 1 orientation. Green ones are 1, 0, 1. And then the blue are the 1, 1, 0. So there's everything you can imagine in between. These are orientated. And then this one is almost like pure, a single crystal oriented in this green orientation, which is somewhere here between 111 and 101. This is our materials of interest. When we ask the system, it gets these diffraction patterns. Tell us what phase it fits. It turns out to be this was cubic titanium nitride. Rest was cubic ferrite. So we can identify phase and the orientation. And the combination techniques give you the full picture. You can do other things. This is what I'm going to tell. It's incredible, actually. So you can do orientation images of, this is a manganese sulfide inclusion that I've been talking about, something like that. I cut them polished in parallel direction. So here you have various orientations on this carbon steel. But you can generate a misorientation image map. Misorientation means the damage and the strain and anything that is not ideal. Well, apparently these areas are highly misoriented, and we found correlation between materials start degrading from these areas that they are mapped here. So we can predict ahead of time without exposing this thing, and we can also tell the quality of the steel. Here is what we think it is. Here is the, before we exposed the surface and did the misorientation image. So every area that's red, yellow, and green are susceptible to the corrosion. That's before we expose this thing to the corrosive environment. And then we expose it to the corrosive environment. Don't ask what kind of environment, anaerobic, highly sulfate, except that the idea is highly corrosive. And look at this. Every place we predicted start corroding. I don't have to run the 6 I can tell you where this thing is going to degrade. If you keep doing it, you know, start having pits and holes around these areas. So we predict, and this is the atomic force microscope image of the same area. You can see the depth of these pits and etc. And then every place on this, I'm almost done. Every place on this image are predicted, like along this manganese sulfide inclusion. This was very short exposure to corrosion. These cementite, these are carbides essentially, making carbon steel hard. Anywhere there's carbide, they start corroding. Even inside, zoom in here, this is a manganese sulfide inclusion. Obviously, it's the immediate surroundings are corroded. And it's exposing this manganese sulfide stringer like that. But it was held together by the the carbon steel matrix. So as soon as the materials are released, it snapped, cracked here and here because suddenly it felt liberated, and then released the stress by simple cracking here and here. This we see quite a lot. Here's the last example. The system predicts that these cementite features, these are carbides, corrode first, and they open up a hole, and then underneath appears to be a manganese sulfide inclusion. If you look carefully, it's a tunnel being dug under the, so that's what happens. Along the manganese sulfide inclusions or stringers, system corrodes, and essentially they join together. You have a hole in the hole of whatever, on the walls of carbon steel. So with that, I would like to conclude. First, integrated OHJ Nanoprobe offers comprehensive analytical capabilities at the same location at the same time. That's very important. These include, but are not limited to, imaging at nanoscale resolution, quantitative elemental information with nanospatial resolution. Field emission microscope, nanospatial resolution imaging were not in spectra because X-rays come from a much bigger volume than size of the beam. But here, OHJ gives you the same elemental information from the size of the beam type of spatial resolution. Here we can do X-ray microanalysis, crystal structure, phase identification, depth profiling, elemental mapping, chemical mapping, limited charge compensation using floating argon ions. Essentially, electrons go on the surface, they charge the surface, we can send in this slow-moving argon ions, they are positive charge, they scavenge electrons. We have limited success, but not total success. And disadvantages include impossibility of using large samples, outgassing of some samples, degrading UHV conditions, longer turnaround times just because of the demand for UHV. Thin film coatings of insulators render OHJ useless, but these are really not that important. At the end of the day, people can bring samples, they are relevant to, they are conducting and all that, but hopefully in the future somebody discovers this carbon graphenes, you coat it, and then our problems, some of these charging problems are, they will become rich, we will become happy. So with that, I will thank you, and I would like to emphasize that this is many years of research put in a short time, and the ONR and NSF, our current NSF and NCI funding, they are gratefully acknowledged. And I thank your time, and then I'm ready for questions if you have any. Did I take, Dave, did I take, oh, hey, I have a thumbs up. Dave liked this, so that's good for me. Anyway, thank you. And then any questions, please do informal. Anybody that's listening, do I talk someplace out there in the internet, ask. Can they ask questions?
They can ask, they can either chat or they can mute themselves.
Do you want me to mute something here?
No, you're over
I'm
there.
okay. Come on, guys, ask questions. Don't be shy. Yeah, Hugo.
This is a room temperature apparatus, or does it have
this particular system has a room temperature apparatus, yes. We didn't have enough money to put a cryo on there, but it's a room temperature. Thank you. I would like to heat sometime and then do some reactions, but for the time being, it's a room temperature. Doesn't mean that we cannot rig it with the heater.
One more question. This is not for insulators. Is there some conductivity limit, or what's the point?
Yeah, some of your samples I worked in the past were a little bit conducting, ion conducting, and things like that. But that's true. We cannot analyze insulators as of yet. We are waiting for inventions by the. So it's conducting materials work best. First, let me have your question, and then I'll have yeah.
So what's your typical yield of auger and characteristics?
I had that and I took it out. I thought it was too much technicality. Oh, he asked if quantum yield of OHJ electrons and the X-ray emission. Very good question. I actually had an answer there, but I didn't want to be too technical. It's like in the low Z elements, X-ray yield is very low, starting from maybe a couple % to, essentially it goes with the Z, increasing Z. OHJ has almost, and then, so for a 15% OHJ yield, they complement each other like that. So yes, at very low Z, starting from lithium actually, you can get OHJ data quantitatively and you can map it and everything. They complement each other. Yeah, Colin, yes, sir.
One, just to comment on the insulators, Nate actually was able to, with thin coats, we still got information from rocks, which are insulators, and so
it's actually excellent good question, excellent comment. The reason you were able to get data because EBSD is a bit more penetrating information because you are using high energy end of the beam, like 20 keV, so they can come out, get information from the 5, 10 monolayers of your sample. So that EBSD not necessarily very surface sensitive. OHJ is surface sensitive because most of the electrons are from 0 to 2,000. EBSD 20,000 EV electrons.
I think though we were getting, I mean, correct me if I'm is Nate back there, or, correct me if I'm wrong, but I thought we got OJ as well from, yeah.
Yeah.
So a little bit, I mean,
depends on the
it's
thickness.
you're not getting that much sample, but yeah, just like, 15 seconds of iridium coat, and then we still got some signal from below.
Of course, that's true, because when I say, attenuation length of say 5 nanometer, it simply attenuates the signal by factor of E, by factor of 3. You still have something escaping through underneath that. Yeah.
So at that comment, and then my other question is: these manganese sulfide, are they what's their habitat? Are they limited to the ferrite, or do they go in both ferrite and cementite, or?
So manganese sulfide inclusions are by design. They are doing this metallurgical process. During the melt, they put extra manganese. For every sulfur, they will put that 20 manganese atoms to scavenge the sulfur. Rest of the manganese are in the iron matrix. You call it solution, I suppose, iron matrix. So there is some manganese in this carbon steel environment, but it is by, I don't know, geologists know these things. You are the experts where you can have manganese sulfide in other environments. I don't know. Yes, please, yeah.
Recep, I'm interested in understanding how you generate diffraction patterns, what
Excellent question. So, repeat. The Robin is asking how we generate this Kikuchi pattern, diffraction patterns. I don't know where I have it, but I have it here. Let me just. This one, these the Kikuchi patterns here, and then take pictures and make sense out of them. So these are taken with these high energy electrons here, 20 keV. So what you do is you tilt the sample about 70 degrees. So the beam comes at 70 degrees to the surface. Just so this is a grazing essentially. The reason this 70 degree tilt is that you want to probe the surface, maybe about 5, 10 layers. Is that Colin does this thing for? Yeah. So you need to have a very good surface, atomically clean surface to be able to So this happens because nature, you know, when they come out, because of this order structure, you cannot help but have this diffraction pattern. And it's a very mature technique. You can immediately, within milliseconds, interpret and tell orientation as well as the phase identification at the submicron, so the resolution. So let's see, resolution can be as small as maybe 20 micron. Is that what's the absolute resolution we get on these things, Nate? So we are talking about nano, submicron to nano scale type of resolutions. So we have here particles, a couple micron size, appropriate for electron backscatter analysis. I think we can get some information on that. I think somebody from your group is asking for that. Yes. Yes.
Recep, what about your sputter rate, and what is the practical depth for profiling in depth that you can do?
Excellent question. So Dave is asking the sputtering rate. So it depends the energy. We have various sputtering rates. We have sputtering rates going from 1 nanometer or maybe half nanometer per minute down to maybe a 20 nanometer per minute kind of. We don't go very deep because when you start sputtering the material, you're actually changing the chemistry and stoichiometry and all these things. So watch out for depth profiling. So typically we do, for example, American Chemet, we are looking for the surface of their copper particles, 1 nanometer. So we have to kind of take it easy, maybe half a nanometer intervals. So sputtering rate depends on the energy of the argon, which we adjust anywhere from, you know, like 500 eV all the way to several thousand eV. So, and the rate goes from sub nanometer per minute all the way with 10 to 20 nanometer kind of per minute rates. Thanks. Yeah. And go ahead. Yeah. Yeah.
So when you do your chemical mapping, like beside using iron oxide, if you put like a soft material under your probe, and can you collect information like what's the carbon percentage, what's the hydrogen percentage?
So not hydrogen. So we OJ can get information from lithium on every Z in the periodic table. But in terms of like doing chemical mapping on these organic materials, this chemical mapping is, I don't want to emphasize it too much. It worked for us, but you have to be, it's a case by case. So if you are interested in combination of 2 or 3 materials, you look at the OJ profile, see if it's different from, say, pure version of one of those components, and then look, it's not easy. So OJ system is not necessarily, when you start going down to these kind of levels, not very easy. But good question. You know, we have to test these ideas. Rama, you had a question. Yes, sir.
So I'm going to be revealing some of my ignorance.
Sure.
Because I'm not a geologist. You talked about crystal structure, phase, and orientation analysis that you are able to do. Crystal structure, I understand. What is the phase and orientation analysis, and how do you do that? Well,
okay, so I will actually ask Dave to answer. Phase actually, so let's take titanium nitride. So it's a titanium nitride, but has different phase. Phase means actually crystal structure. Is it a cubic or is it a hexagonal? So that's what I mean by, say, phase identification. That's what I mean. So maybe I misrepresented.
And the orientation?
Orientation is the orientation at that particular location. It may be different 1 micron later.
I'm not going to look at data.
Yeah, so for example, EDS will tell you you have calcium, carbon, oxygen. You need to know, is it aragonite or calcite? That's exactly what we need to do.
So phase identification
yes.
can differentiate between these two. Thanks. Any other questions before?
Recep, can you hear me from the ether?
Oh, yes, I hear you very well. Please, can you identify yourself, please?
Recep, this is Alexi. I apologize. I meant to join in person, but here I am.
Sure.
Can others hear me?
You can ask anything you want, including
Can the rest of the group hear me?
I hear you.
Yeah,
Okay.
very well.
So my question's a little bit more on the practical side. Can you give some suggestions as to elemental analysis when your expected like concentrations are relatively low? You know, so when you have maybe 1-2% concentrations, like this is more of a signal to noise question, I guess. But
Yes, thank you for asking that. Actually, I should have mentioned it now that Robin is in the audience. So OHJ and the X-ray spectroscopy is not for trace element analysis. You have to go to the next level for that. So it's ICMS, you know, laser ablated mass spectroscopy technologies and things like that can do sub percentage type of even part per million to billion to trillion. But in OHJ and X-ray analysis, we are talking about maybe a couple percent. So this falls into, so you're in the gray area. A couple percent, yes, we can do quantitative analysis, relative quantitative analysis. The systems are not really meant to be absolute quantitative analysis. So we can tell within maybe a couple percent sensitivity what is there. But if you would like to go more than that, unfortunately, you cannot do that. So you cannot analyze, say, 0.1%, you know, and then, you know, probably there will be 100% error in that. So a couple percent is okay. We can do, and we can even find them. Here is an example, for example. This is something here. Right here, this manganese sulfide inclusion has titanium. Overall, you will not see too much, but if it is localized like that, I can 100% analyze these kind of things. Are you seeing this maybe or not?
Yeah, I see it.
Okay, so if these materials of interest, elements of interest are localized, not, you know, a solution in a solid, yes, we can do very good job by mapping it first and then attacking it that way. But if it is a solution of one element into another element, then we are talking about maybe a couple percent at the best.
Sure.
I hope I answered. Is that,
yeah, that's very helpful.
Yeah. Thank you. So, any other questions from internet?
Yes, actually, Recep, this is Robert Silagi from the chemistry department.
Yes, sir.
I have a question about the resolution related to the chemical analysis. So I assume that you can see differences, let's say, with an iron 3 and iron 2 oxidation state, but can you go even higher resolution, seeing differences like high spin, low spin, different crystal field splitting?
Thanks for that question. This is an important question. It's about chemistry. Be honest with you, OHJ is not as good to determine the chemical structure, I mean, chemical status of a given ion, whether it's iron 2 or whether it's, I don't know, whatever materials you're working with, iron 3. It is not trivial in OHJ. We have to analyze it case by case and get some reference control materials and then compare it just like what we did in our manganese oxide and then iron oxide mapping. It's the XPS there you can have a bit better chance, but XPS doesn't have this kind of image resolution. So unfortunately, you have to do it differently. For example, we combine this EBSD with elemental analysis and to see to see certain crystal structures and compound. But I am not going to be very helpful, unfortunately, in terms of chemical, the shifts or the ionicity or whatever you're interested in with OHJ. It should be done case by case basis. So just bring out your samples and see if we can make sense out of it. But it won't help. You're asking most difficult things that we can do. But thank you for that. Those are the limitations of this technology.
Thank you, Recep. I have the samples, so we can talk about it.
Sure, anytime. Thank you. All right. Well, if you have no other questions, I thank you for your time, and you have a wonderful rest of the day. I even have 5 minutes to spare for lunch. Thank you.
Thank you.